Welcome to Distributed System course. In the previous session, we discussed Lambert's mutual exclusion algorithm. In this section, we are going to discuss RICART-AGRAWALA mutual exclusion algorithm. We have to achieve mutual exclusion among a collection of processes so as to coordinate their actions, or we can coordinate their access to shared resources. That is, only one process is allowed to execute the critical section at any given instant of time. The action performed by user on shared resources must be atomic. In distributed system, we neither have shared memory or common physical clock, and therefore we cannot solve mutual exclusion problem using shared variables. To eliminate the mutual exclusion problem or solve the mutual exclusion problem in distributed system, we are going to use the message passing. We already discussed some of the mutual exclusion algorithms. The distributed mutual exclusion algorithms are Lambert's algorithm, RICART-AGRAWALA algorithm, Mikawa's algorithm, and Suzuki-Kasami broadcast algorithm. You already discussed Lambert's mutual exclusion algorithm in the previous session. Today we are going to discuss RICART-AGRAWALA algorithms. The remaining two algorithms will be discussed in the upcoming sessions. First of all, the system model. The distributed system consists of n sites numbered S1, S2, S3 up to Sn. We assume that a single process is running on each site. The process at a site SA is denoted by Pi. A particular site may contain more than one process. We are denoting it by using some number, that is a Pi. A site can be in one of the three states. That is, a particular way considering a particular site, it can be in any one of the three states. First state is requesting the critical session. Second one is the executing the critical section. The third one is neither executing nor neither requesting nor executing the critical section. You can say that it is an ideal state. In the requesting the critical session state, the site is blocked and cannot make further request for critical session. That is, it can only request only one request to enter the critical session. At the same time, it cannot request for another critical session. In the ideal state, the site is executing the outside the critical session. The third one, then in the executing critical session state, the particular process is in and is executing the critical session part of that process. At any instant, a site may have several pending requests for critical session. A site requests the request from various sites or process. A site queue up these requests and serve them one at a time. We already discussed how the Lambert's mutual exclusion algorithm is working. Here also it is another algorithm, that is RICART-AGRAWALA algorithm, also based on that. It is also a non-token based approach. To use a non-token based approach in the RICART-AGRAWALA algorithms. That is, the RICART-AGRAWALA algorithm assume that the communication channel are FIFO, that is first in, first out. The algorithm uses two types of message. The first one is the request and the second one is reply. When we compare the RICART-AGRAWALA algorithm with the Lambert's algorithm, the Lambert's algorithm contains three type of messages: request, release, and reply. Then it contains only two messages, that is request and reply. A process send a request message to all other process to request their permission to enter the critical session. A process send a reply message to a process to give its permission to that process. So it is one is used for requesting and another is used for to give the reply. The RICART-AGRAWALA algorithm is an optimization of Lambert's algorithm that it dispenses with a release message by cleverly merging them with a reply message. That is, here we are using two messages, that is a request and a reply messages, not using the release message. The RICART-AGRAWALA algorithm is one of the optimization of already says the Lambert's algorithm. In this RICART-AGRAWALA algorithm, that optimize, or we can say that it dispenses with the release message by cleverly merging them with reply message. That is, we are not sending the reply message, we are merging that release message. We are not sending the release message, we will include, or we will piggyback the particular release message with the reply message. That is the idea of RICART-AGRAWALA algorithm. So that is why we are using only two type of messages instead of three type of message. The processes uses the process in the RICART-AGRAWALA algorithm uses a Lambert style logical clock to assign timestamp to critical session requests, and timestamps are used to decide the priority of request. The same thing that is applied in the logical mutual exclusion algorithm is also adapted in RICART-AGRAWALA algorithm. In addition to that, each process PI maintain a request deferred the request deferred array that is denoted by RD of I. That is it is the request deferred array of process I. Initially, all the values of the request deferred array is set to 0. The size of the request deferred array is same as the number of processes in the system. If the system contains n process, then the size of each and every request deferred array in each and every process is n. The size of the request deferred array depends on the number of processes in the system. Initially, all the values of the request deferred array is set to 0. So if we consider a particular process PI, for that process we will set all the values of the array to 0 in the initial case. It will be performed for each and every process in the system. Whenever PI defer the request by PJ, it is set the deferred position of the particular request deferred array to 1. That is, when a particular process PI defer the request sent by PJ, that is PJ want to enter the critical session, so it will send the request to PI. So PI will defer the request, and it will set the corresponding entry in the request deferred array to 1. That is the RDI. RDI means the process PI's request deferred array. Then its corresponding position is indicated by the index value, that is J, that is correspond to process J. We are going to deny or defer the request sent by process PJ, so we will set the value at a RDI of J. J means we are going to defer the request from process J, so we will set the corresponding entry in the process PI as RDI of J equal to 1, where J is the requested process, I is the other process which deny or defer the request. After PI has sent a reply message to PJ, then after some times it may give permission to PJ by giving a reply message to PJ. So on that time we will modify the entry of the request deferred array to 0. That is we will reset it to 0. That is the idea here. In addition to the request deferred array, we are using a queue for maintaining the request from various processes. The record Agarwala algorithm contains three sections. That is, first section is requesting the critical session, then second one is the executing the critical session, then last one is the release the critical session or exiting the critical session. When a site in the requesting section, when a site SA want to enter the critical session, it broadcasts the timestamp request message to all other sites. When the site SJ receive a request message from site SI, it send a reply message to the site SI if the site SJ is neither requesting nor executing the critical session. That is the first condition. If a particular process SJ receive a request message from site SJ to enter the critical session, it is send a reply message only if it is not requesting the critical session or nor executing the critical session. Both the case. That is, if a RJ is requesting, it may deny the request to enter the critical session. Also at the same time, if it is executing the critical session, it also deny the request from that particular process PA. That is the first condition. Or it may send the reply message, or the SJ will send a message to SI if the site SJ's timestamp is larger than the timestamp of SI. That is, we will give permission to enter the critical session based on the timestamp. If the timestamp of the requesting process is smaller compared to its own timestamp, then we will give the reply message. Otherwise, we will defer the reply. That is the idea. If the requesting process are higher or larger timestamp, then we will not send any reply message to it. That is the idea. Then we will if the timestamp is smaller, then we will give higher priority. If the timestamp is higher, then we will that particular process have lesser priority than other process. That is the idea of this RICART Agarwala algorithm. Then come to the next section, that is RICART Agarwala's next section, that is executing the critical session. Site SI enter the critical session after it has received a reply message from every site. That is, a particular process site at PSI can enter the critical session only after receiving a reply message from each and every sites in the system. Then next section is releasing the critical session. When the site SA exits the critical session, it is send a reply message to all the deferred requests. We are storing the deferred request in the queue. For that processes, we will send the reply message after exiting the critical session. When site SA exit the critical session, it is sent the deferred reply, that is the delayed reply to all the process. Also at the same time, we will change the request deferred array values. For if we send a particular reply to process SJ from SI, then we will change the entry for process J in the deferred request deferred array of particular process pi. For every j, if we sending the particular process for a particular process pj, if we send a message, that is reply message, then we will change the entry of that particular process in process pi request deferred array. That is in the previous it is 1, so we will reset it to 0. That is the case. Consider one example to understand the working of these RICART-AGRAWALA algorithms. We are here, the system contains 3 processes, P1, P2 and P3. So at the same time, each and every process contains a request deferred array, which is numbered request deferred array 1 and request deferred 2 and request deferred array 3. Then the size of the request deferred array is based on the number of processes in the system. So this system contains 3 processes. So the size of the request deferred array equal to 3. So you can see here each and every array contains 3 positions. The first position corresponds to process 1, the second position corresponds to process 2, then third position corresponds to process 3. In each and every you can see the each and every process contains a request deferred array with the same size. That is the number of processes in the system. We assume that the processor, the location of each and every process is in the process number basis. That is first position for process 1, then second position for process 2, then third position for process 3. Initially, we are set the values of all the entries or all the locations of this array to 0, because there is no deferred reply at all. So we will set the value to 0 in the first case. Then the process P3 want to enter the critical session, so it will execute the requesting the critical session part. So requesting the critical session, it will send all the it will send the request message to all other processes in the system. That is, it will send a request message to the process P1 and P2. So P3 want to enter the critical session, so it send a request message to all other process, that is P1 and P2. That request message contains the timestamp and the process number. It is we already discussed the Lembolt logical clock. This algorithm also working based on the Lembolt's logical clock. So the timestamp, the first event in this particular system is the P3's first event, that is sending a request to enter the critical session. So we will assign the timestamp 1 to that particular event, the requesting event or sending event. We are going to give 1. So the timestamp of the request message contains value 1 and the process number is P3. P3 is going to send the message to other process. That is requesting. That is about the requesting session. Then at the same time, after some times, the particular process P1 want to enter the critical session. So the process P1 also sent a request message which contains the timestamp and the process number. According to Lembolt's logical clock, the timestamp of the P1 is equal to 2. That is, it is a second event happened in the system. So we will set the value timestamp to 2, and it also contains the process number P1. That request message is sent it to all other process, that is P2 and P3. Then the process P1 receive a request to enter the critical session from P3. Also same time the P2 receive the request to enter the critical session from P1 and P3. the P3 receive a request message to enter the critical session from P1. So in the requesting session, we will give permission to enter the critical session only if its timestamp is the requested process timestamp is lesser than its own timestamp. So we will compare it the values of timestamp, and then we will give permission or deny the permission to enter the critical session. If we consider the process P1, if we consider the process P1, it will receive a request from the process P3. It contains the timestamp 2. So we will compare the P1's timestamp and the P3 timestamp to decide whether to give the permission to the P3 or not. So the timestamp of P3 is lesser than the timestamp of P1. So we will give permission to enter the critical session to P3. That is, we are comparing the 1 and 3. 1 is the times 1 and 2. The 1 is the timestamp of process P3, and 2 is the timestamp of P1. So the process which have the less timestamp is P3. So P1 will give permission to enter the critical session to P3. So P1 can send reply message to P3. When come to the P2, P2 is not neither requesting in the critical session, not executing the critical session. That is, it is not requesting or nor neither requesting the critical session, nor executing the critical session. So it will send a reply message to the two process, that is P1 and P3. When come to the P3, then P3 have the request from P1 to enter the critical session. So P3 will compare its timestamp, that is its timestamp is 1 and P1 timestamp is 2. So its timestamp is smaller than the requesting timestamp, requesting process timestamp. So we will defer the reply. That is the idea of this RICART AGRAWALA algorithms. Then we will defer the reply to process P1, and we will set the corresponding request deferred arrays value to 1 for that particular process. That is the first location. That is, first location is used for P1. So we will set the value to 1. Before it is 0. Initially it is 0, it was 0. Now we will set the values to 1 because we are going to defer the reply to process P1. Then we will queue up these requests in one of the queue maintained in the process P3. That is, you can see in the figure, the Q3 contains the request message, that is timestamp, including the timestamp 2 from the process P1. So P1 can give reply to P3, and P2 can reply to P1 and P3, but P3 defer the reply to P1. That is the idea. Then after receiving all the requests from process P1 and P2, the P3 can enter the critical session. So it will receive, that is executing part, the section, a process can enter the critical session only after receiving messages from P1 and P2. So the P3 can enter the critical session. Then after executing the critical session, the process P3 will reset its corresponding value in the request deferred array to 0. That is, it is going to send the reply message to P1. So it will delete the entry in the queue, that is correspond to the process P1. We will delete the queue, so the queue will become empty. Also at the same time, we are going to reset the value to 0 in the position of, that is particular position of that is first position of RD3. That is the idea. So on exiting the critical session or releasing the critical session, a particular process will send the reply to the deferred reply to the all the process in the queue. At the same time, it will change the values in the request deferred array. That is the idea. Then now the process P1 get the reply message from all other process, that is P2 and P3, so it can enter the critical session. After finishing, there is no the process waiting to enter the critical session. So any process can request the critical session after the execution of P1. It will working in the same principle. Okay. Then come to the requirement of mutual exclusion algorithms. First one is the safety property. Safety property says that at any instance only one process can execute the critical session. Here only one process is executing the critical session at a time because it is based on the timestamp. No two processes can have the same timestamp. Then we will give priority to the lower number timestamp. So only one process can execute its critical session in RICART-AGRAWALA algorithm. So safety property is satisfied here. But come to the liveness properties, it deals with no deadlock and no starvation. But in RICART-AGRAWALA algorithm, there is a chance of deadlock. Deadlock means the two or more sites should not endlessly waiting for messages which will never arrive. That is, if you consider one situation, that is after executing the critical session, if the process P3 go to crash, then the process P1 will endlessly waiting for message from the process P3. That is going to be the deadlock situation. So it can be happen in the RICART-AGRAWALA algorithm. So RICART-AGRAWALA algorithm is prone to the deadlock. Then there is no starvation because each and every process will get based on its timestamp. We will assign the same timestamp. We will assign the timestamp based on logical Lembert's clock. There is no chance of starvation in this RICART-AGRAWALA algorithm. Then the next property is the next requirement is fairness. That is, fairness means that the critical session execution requested are executed in the order of their arrival time. That is here based on the logical time. So we are assigning we are giving the permission to enter the critical session based on the only the timestamp, the logical timestamp. So there is no no chance of in order, or we can say that there is we guarantee that there is a fairness. That means in RICART-AGRAWALA algorithm, all the processes are executed in the order of their arrival. That is the case. Then come to the performance metrics. Here are only two type of messages. First one is request message and a reply message. To enter a particular critical session, a process want to send some messages. The message complexity says that the number of messages required per critical session by a site. So to enter a critical session, a site can send n-1 request. That is, it need to send n-1 request to all other process. So it need to send the request message to n-1 process. So the number of request message is n-1. Also it need the reply from all the n-1 process. So it contains n-1 reply messages also. So totally 2 into n-1 messages per critical session are needed for the particular site to enter the critical session. That is the message about the message complexity. The synchronization delay also the T. Based on this, we can calculate the throughput also, that is 1 divided by the synchronization delay plus average critical session execution time. We can optimize this algorithm, RICART-AGRAWALA algorithms, by some tricks. That is, in RICART-AGRAWALA algorithm, if one process wants to enter the critical session, then it is send a request message to all other processes in the system. After receiving all the reply messages, that process can enter the critical session. If the same process want to enter the critical session once again, it need to send the request message to all other process again. If if no other process want to enter the critical session, then also we need to send the request message to all other process. So the RICART and Carvalho optimizes the RICART-AGRAWALA algorithm by observing that once a site Si has received a reply message from a site Sj, the authorization implicit in this message remains valid until Sa sent a reply message to Sj. That is the idea. That means a particular process need a request the permission to enter the critical session. If a particular process want to enter the critical session, it need permission from all other process. That authentication, that we will give an authentication. That authentication will remain valid until the corresponding requested process send a reply message to all other process. That is the idea. Here, if the process P1 want to enter the critical session again after executing the first critical session, if it want to enter the critical session again, then it can enter the critical session without sending any messages, without sending any reply messages, request message to all other process. That is the idea. The authorization implicit in this P1 remains valid until the S1, that is P1 will send the reply message to all other process, which happens only after the reception of the request message from that particular process, that particular process P2 and P3. So here the process P1 can enter any number of times without sending the request message. So once the particular process P1 send a reply message to process P1 or P2, then only if after that, if it need to enter the critical session again, it is needed to send the request message. So up to the P1 sent the reply message to P1 or P2 or P3, it can enter the critical session. That is one modification made by the two scientists in RICART-AGRAWALA algorithms. So the number of request message and the reply message will decrease in this situation. That is, it is sometimes some situation it is need not to send any message to enter the critical session. In some situation it need to send n-1 message to enter the critical session. So in both of the case of reply and request, it may be varying from 0 to n-1. So in the modified or optimized RICART-AGRAWALA algorithm, the message complexity will be 0 to 2 into n-1, because it needs 0 to n-1 request message, also 0 to n-1 reply message. So it is in the range of 0 to in between 0 to 2 into n-1 messages per critical session. The synchronization delay remains the same in the case of the actual RICART-AGRAWALA algorithms. So that is about the RICART-AGRAWALA algorithms. In the next session, we will see the Mikos mutualist algorithm in detail. Thank you.